All right, so we're going to work out this optimization problem. This is a very interesting one. I have done a few in separate videos. Please check this out before you try to do this problem. Also, you can pause the video and work it out first before you take a look at the answers that I'm about to show you. So let's take a look. So a certain airline requires that a rectangular package is carried on an airplane by passengers be such that the sum of the three dimensions is at most 120 centimeters. We want to find the dimensions of the square-ended rectangular package of the greatest volume that meets this requirement. All right, so let's consider drawing a rectangular box. So let's suppose this is our package or carry-on or whatever you want to call it. That's the box. I'm going to try to make it a 3-dimension so you can visualize this. So say you're looking at something like this. Sorry, not the best picture. Let's call this 3-dimensional box right here. So so the sides, so this side and this side, they're going to be a square. So I'm going to go ahead and put the dimension here. This and this would be X, and then this length right here, this would be Y. So on the side, they're going to be a square, and the entire box is a rectangle. So the dimension for this particular object will be X plus Y. And we know it cannot be more than 120, so we'll say this is equal to 120, which means that you can combine X and X since they are like terms. This will be 2X plus Y equals to 120. And then here you can solve for one of the variable, either X or Y. I'm going to go ahead and solve for Y. So Y would be 120 minus 2X. Now hold on to this equation because this is going to be your helping equation for your objective function. So we're going to call this our constrained equation or your helping equation to that will help you to optimize this particular object. So we want to find the greatest volume that meets this requirement. So meaning our objective function will be the volume function. So our objective equation for this particular problem will be the volume. We know volume is length times width times height. So here our length, you can call it the height, and the width are X and X, and the length would be Y. So you have X times Y. So that means your volume now is a function of two variables. Volume is equal to X squared Y. Now, since we're going to be taking the derivative of this function, we want to convert this into a single variable function, rather two variables function. So we're going to here apply our constraint so that it becomes a function of a single variable. So then our volume will simply be X squared Y. Y we know using the constraint equation is 120 minus 2X. And here you can distribute out to simplify the volume function before taking the derivative. Your volume is 120X squared minus 2X cubed. All right, so that's the one you're going to be taking the derivative of and finding the critical numbers. Okay, so far, so good. I hope this makes sense. Now let's take the derivative. So the derivative of v respect to x, this is going to be, so 120 times 2, you're going to get 240x minus 3 times 2, that's going to be 6x squared. And then we're going to set it to 0. So that means when you set it to 0, you can factor out a common factor. That'll be 6x times 40 minus x equal to 0. And then set each component to 0 to get the critical numbers. So you'll have 6x equals to 0 and 40 minus x equal to 0. But if 6x is equal to 0, that means x is equal to 0. So that wouldn't make sense in this problem. So that means we have to look at x is equal to 40. So that's our dimensions. For x, we need to find y. Now, before that, you want to check that this gives you the greatest or the maximum value of this particular object. So we're going to verify that by the second derivative test. So let's go ahead and take a look at the second derivative. So let's go ahead and take the derivative of that. So the second derivative would be 240 and 40 minus 12x, and then and here if we set it to 0, we get possible inflection points, but they're not needed right now. What I want you to notice here is that your second derivative at x equals 40 at the critical number, it's going to be less than 0. So I want you to verify that and look at that. And that would indicate that our function is going to be concave down. So when we concave down curve, that means we do have a maximum at that critical number. So this will give us the maximum value of this particular object. All right, so we're almost done with the problem. We know x has to be 40 centimeter. Now, how do we find y? Well, we get y from this constraint equation. So the dimension are going to be the following. So x is 40. That means y has to be 120 minus 2 times x. That would be 40. So that would give you y is equal to 120 minus 80. That would be also 40. So the dimension for this particular luggage has to be 40 by 40 by 40. Okay, I hope this helped you. I hope you got the same answer as me. So take care, everyone.